Welcome back. In this session, we will discuss factorization of polynomials over a field. In mathematics and computer algebra, polynomial factorization refers to factoring a polynomial into irreducible polynomials over a given field. In this session, we first consider division algorithm for the ring f of x, where f is a field. We will discuss some results and examples that follow from division algorithm. We define irreducible polynomial and illustrate the term through examples. We will describe Eisenstein polynomial and we will see that if a polynomial is in the form of Eisenstein polynomial, then it is irreducible. We will describe the existence and uniqueness theorem for representing a given polynomial into a product of irreducible except for unit and for order. Division algorithm for the ring f of x. Theorem 1. Division algorithm for the ring f of x. Let f be a field and f of x equal to a n x raised to n plus a n minus 1 x raised to n minus 1 plus etc. a naught, and g of x equal to b m x raised to m plus b m minus 1 x raised to m minus 1 plus etc. b naught be two elements of the ring f of x, with a n and b m both non-zero elements of f and m greater than 0. Then there are unique polynomials q of x and r of x in f of x such that f of x equal to g of x into q of x plus r of x, with the degree of r of x less than the degree m of g of x. Proof. Consider the set S equal to f of x minus g of x into s of x such that s of x belongs to f of x. Let r of x be an element of minimal degree in S, then being an element in S, we can write r of x in the following form. R of x equal to f of x minus g of x into q of x for some q of x belongs to f of x. Hence, f of x equal to g of x into q of x plus r of x. We must show that the degree of r of x is less than m. Suppose that r of x equal to ct x raised to t plus ct minus 1 x raised to t minus 1 plus etc. plus c naught, with cj belongs to f and ct not equal to 0 if t not equal to 0. Suppose t greater than or equal to m, then f of x minus g of x into q of x minus ct by bm into x raised to t minus 1 into g of x, which is equal to r of x minus ct by bm into x raised to t minus m into g of x, equation 1. And the later is of the form r of x minus ct x raised to t plus terms of lower degree, which is a polynomial of degree lower than t, the degree of r of x. However, the polynomial in equation 1 can be written in the form f of x minus g of x into q of x plus ct by bm into x raised to t minus m. So, it is in S, contradicting the fact that r of x was selected to have minimal degree in S. Hence, our supposition t greater than or equal to m is wrong. Hence, this gives t less than m. Thus, the degree of r of x is less than the degree m of g of x. For uniqueness, if f of x equal to g of x into q1x plus r1x and f of x equal to g of x into q2 of x plus r2 of x, then subtracting we have g of x into q1 of x minus q2 of x, which is equal to r2 of x minus r1 of x. Since the degree of r2 of x minus r1 of x is less than the degree of g of x, this can only hold if q1 of x minus q2 of x equal to 0 or q1 of x equal to q2 of x. Then we must have r2 of x minus r1 of x equal to 0 or r1 of x equal to r2 of x. Corollary 1. Factor theorem. An element A belongs to f is a 0 of f of x belongs to f of x if and only if x minus a is a factor of f of x in f of x. Proof. Suppose that for a belongs to f, we have f of a equal to 0. By the division algorithm, there exists q of x and r of x such that f of x equal to x minus a into q of x plus r of x, where degree of r of x is less than 1. Then we must r of x equal to c for c belongs to f. So, f of x equal to x minus a into q of x plus c. Applying evaluation homomorphism phi of a from f of x to f, we obtain phi of a of f of x equal to phi a of x minus a q of x plus c, that is f of a equal to a minus a into q of a plus c. Since f of a equal to 0, the above gives 0 equal to c, that is c equal to 0. Then f of x equal to x minus a into q of x. So, x minus a is a factor of f of x. Conversely, if x minus a is a factor of f of x in f of x where a belongs to f, then applying evaluation homomorphism phi a to f of x equal to x minus a into q of x, we have f of a equal to 0 into q of a equal to 0. Corollary 2. A non-zero polynomial f of x belongs to f of x of degree n can have at most n zeros in a field f. The preceding corollary shows that if a1 belongs to f is a 0 of f of x, then f of x equal to x minus a1 into q1 x, where of course the degree of q1 of x is n minus 1. If a 0 a2 belongs to f of q1 x, then results in a factorization f of x equal to x minus a1 into x minus a2 into q2 of x. Continuing this process, we arrive at f of x equal to x minus a1 etc. x minus ar into qr of x, where qr of x has no further zeros in f. Since the degree of f of x is n, at most n factors x minus ai can appear on the right hand side of the preceding equation. So, r less than or equal to n. Also, if b not equal to ai for I equal to 1 to etc. r and b belongs to f, then f of b equal to b minus a1 etc. b minus ar into qr of b not equal to 0, since f has no divisors of 0 and none of b minus ai or qr of b are 0 by construction. Hence, the ai for I equal to 1 to etc. r less than or equal to n are all the zeros in f of x. The following result is taken from group theory. Theorem 2, fundamental theorem of finitely generated abelian groups. Every finitely generated abelian group G is isomorphic to a direct product of cyclic groups in the form set p1 raised to r1 cross set p2 raised to r2 cross etc. set pn raised to rn cross set etc. set, where pi are primes not necessarily distinct. The direct product is unique except for possible rearrangement of the factors. In particular, a finitely generated finite abelian group G is isomorphic to a direct product of cyclic groups in the form set p1 raised to r1 cross set p2 raised to r2 cross etc. set pn raised to rn. Corollary 3. If G is a finite multiplicative subgroup f star dot of the multiplicative group of a field f, then G is cyclic. In particular, the multiplicative group of all non-zero elements of a finite field is cyclic. Proof. Applying theorem 2, being a finite abelian group, G is isomorphic to a direct product set d1 cross set d2 cross etc. set dr, where each di is a power of a prime. Let us think of each of the set di as a cyclic group of order di in multiplicative notation. Let m be the least common multiple LCM of all the di for I is equal to 1 to etc. r. Note that m less than or equal to d1 into d2 etc. dr. If ai belongs to set di, then ai raised to di equal to 1. So, ai raised to m equal to 1 since di divides m. Thus, for all alpha belongs to G, we have alpha raised to m equal to 1. So, every element of G is a 0 of x raised to m minus 1. But G has d1 into d2 into etc. dr elements, while x raised to m minus 1 can have at most m zeros in the field f by corollary 2. So, m greater than or equal to d1 into d2 etc. dr. Hence, m is equal to d1 into d2 into etc. dr. So, the primes involved in the prime powers d1, d2 etc. dr are distinct, and G is isomorphic to the cyclic group Zm. Example 1. Consider Z 5x, the ring of all polynomials in the indeterminate x over the field Z5. Applying division algorithm to f of x equal to x raised to 4 minus 3x cube plus 2x square plus 4x minus 1 belongs to Z5x, and g of x equal to x square minus 2x plus 3 belongs to Z5x. Solution. The long division should be easy to follow, but remember that we are in Z5x. For example, 4x minus 3x equal to 2x. X raised to 4 minus 3x cube plus 2x square plus 4x minus 1 divides x square minus 2x plus 3. Consider x square, it gives x square into x square minus 2x plus 3 gives x raised to 4 minus 2x cube plus 3x square. Subtracting, we obtain minus x cube minus x square plus 4x. When divided by minus x, we obtain minus x into x square minus 2x plus 3 gives minus x cube plus 2x square minus 3x, which gives minus 3x square plus 2x minus 1. Take minus 3 upper side, minus 3 into x square minus 2x plus 3 gives minus 3x square plus x minus 4. Subtracting, we obtain x plus 3. Thus, q of x equal to x square minus x minus 3 and r of x equal to x plus 3. Example 2. Working in Z5x by substitution, it can be seen that 1 is a 0 of x raised to 4 plus 3x cube plus 2x plus 4 belongs to Z5x. Thus, by corollary 1 of division algorithm theorem, we should be able to factor x raised to 4 plus 3x cube plus 2x plus 4 into x minus 1 into q of x in Z5x. Let us find the factorization by long division. X raised to 4 plus 3x cube plus 2x plus 4 divides x minus 1 First take x cube into x minus 1 gives x raised to 4 minus s cube. Subtracting, we get 4x cube. Consider 4x square. 4x square into x minus 1 gives 4x cube minus 4x square. Subtracting 4x square plus 2x. Take 4x, then 4x into x minus 1 gives 4x square minus 4x. Subtracting, we obtain x plus 4. Then take 1 and multiply 1 by x minus 1 gives x minus 1. Subtracting, we obtain it is equal to 0. Thus, x raised to 4 plus 3x cube plus 2x plus 4 equal to x minus 1 into x cube plus 4x square plus 4x plus 1 in Z5x. Since 1 is seen to be a 0 of x cube plus 4x square plus 4x plus 1, also we can divide this polynomial by x minus 1 and get x cube plus 4x square plus 4x plus 1 divides x minus 1. Take x square into x minus 1 gives x cube minus x square. Subtracting, we get 0 plus 4x plus 1. Take 4 into x minus 1 gives 4x minus 4. Subtracting, we get 0. Since x square plus 4 still has 1 as 0, we can divide again by x minus 1 and get x square plus 4 divides x minus 1. Take x into x minus 1 which is equal to x square minus x. Subtracting, we obtain x plus 4. Take 1 into x minus 1, we obtain x minus 1. Subtracting, we obtain it is equal to 0. Thus, x raised to 4 plus 3x cube plus 2x plus 4 equal to x minus 1 whole cube into x plus 1 in Z5x. Irreducible polynomial. Definition. Irreducible polynomial. A non-constant polynomial f of x belongs to f of x is irreducible over f or is an irreducible polynomial in f of x if f of x cannot be expressed as a product g of x into h of x of two polynomials g of x and h of x in f of x, both of lower degree than the degree of f of x. Example 3. Since x square equal to 2 has no solution in Q, the polynomial x square minus 2 belongs to Q of x has no zeros in Q. This shows that x square minus 2 is irreducible over Q. For a factorization, x square minus 2 equal to x plus b into cx plus d for a, b, c, d belongs to Q would give rise to zeros of x square minus 2 in Q. However, x square minus 2 viewed in R of x is not irreducible over R because x square minus 2 factors in R of x into x minus root 2 into x plus root 2, product of two lower degree polynomials. Example 4. Show that f of x equal to x cube plus 3x plus 2 belongs to Z5x is irreducible over Z5. Solution. If x cube plus 3x plus 2 factored in Z5x into polynomials of lower degree, then there would exist at least one linear factor of f of x of the form x minus a for some a belongs to Z5x. But then f of a equal to 0 by corollary 1 of division algorithm. However, f of 0 equal to 2, f of 1 equal to 1, f of minus 1 equal to minus 2, f of 2 equal to 1 and f of minus 2 equal to minus 2, showing that f of x has no 0 in Z5. Thus, f of x is irreducible over Z5. Remark. The test used in the above example for irreducibility by finding zeros works nicely for quadratic and cubic polynomials over a finite field with a small number of elements. Theorem 3. Let f of x belongs to f of x and let f of x be of degree 2 or 3. Then f of x is reducible over f if and only if it has a 0 in f. Proof. If f of x is reducible so that f of x equal to g of x into h of x, where the degree of g of x and the degree of h of x are both less than the degree of f of x, then since f of x is either quadratic or cubic, either g of x or h of x is of degree 1. If say g of x is of degree 1, then except for a possible factor in f, g of x is of the form x minus a. Thus, g of a equal to 0, which implies that f of a equal to 0. So, f of x has a 0 in f. Conversely, corollary 1 of division algorithm theorem shows that if f of a equal to 0 for a belongs to f, then x minus a is a factor of f of x. So, f of x is reducible. We now state an important result. Theorem 4. If f of x belongs to z of x, then f of x factors into a product of two polynomials of lower degrees r and s in q of x if and only if it has such a factorization with polynomials of the same degrees r and s in z of x. Corollary 4. if f of x equal to x raised to n plus a n minus 1 x raised to n minus 1 plus etc. plus a naught belongs to Z of x with a naught not equal to 0, and if f of x has a 0 in Q, then it has a 0 m in Z, and m must divide a naught. Proof: if f of x has a 0 a in Q, then f of x has a linear factor x minus a in Q of x by corollary 1 of division algorithm theorem. But then by the previous theorem, f of x has a factorization with a linear factor in Z of x. So, for some m belongs to Z, we must have f of x equal to x minus m into x raised to n minus 1 plus etc. plus a naught by m. Thus, a naught by m belongs to Z. So, m divides a naught. Example 5. The above corollary gives us another proof of the irreducibility of x square minus 2 over q for x square minus 2 factors non-trivially in q of x if and only if it has a 0 in q by theorem 3. By the corollary above, it has a 0 in q if and only if it has a 0 in Z, and moreover, the only possibilities are the divisors of plus or minus 1 and plus or minus 2 of 2. A verification shows that none of these numbers is a 0 of x square minus 2. Example 6. Show that f of x equal to x raised to 4 minus 2x square plus 8x plus 1 viewed in q of x is irreducible over q. Solution: if f of x has a linear factor in q of x, then it has a 0 in Z, and by corollary 4, this 0 would have to be a divisor in Z of 1, that is either plus or minus 1, but f of 1 equal to h, f of minus 1 equal to minus h. So, such a factorization is impossible. If f of x factors into two quadratic factors in q of x, then by the previous theorem, it has a factorization x square plus ax plus b into x square plus cx plus d in Z of x. Equating coefficients of powers of x, we find that we must have bd equal to 1, ad plus bc equal to h, ac plus b plus d equal to minus 2, and a plus c equal to 0 for integers a, b, c, d belongs to Z. From b into d equal to 1, we see that either b equal to d equal to 1 or b equal to d equal to minus 1. In any case, b equal to d, and from a into d plus b into c equal to h, we deduce that d into a plus c equal to h. But this is impossible since a plus c equal to 0. Thus, a factorization into two quadratic polynomials is also impossible, and f of x is irreducible over q. Eisenstein Polynomial. Theorem 5. Eisenstein Polynomial. Let p belongs to Z be a prime. Suppose that f of x equal to a n x raised to n plus a n minus 1 x raised to n minus 1 plus etc. plus a naught belongs to Z of x, and a n not congruent to 0 mod p, but a I congruent to 0 mod p for I less than n with a naught not congruent to 0 mod p square. Then f of x is irreducible over q, that is, if p divides a I for I less than n, p does not divide a n and p square does not divide a naught of the polynomial f of x equal to a n x raised to n plus a n minus 1 x raised to n minus 1 plus etc. plus a naught belongs to Z of x. Then f of x is irreducible over q. Proof: by theorem 4, we need only to show that f of x does not factor into polynomials of lower degree in Z of x. If f of x equal to br x raised to r plus etc. plus b naught into cs x raised to s plus etc. c naught is a factorization in Z of x with br not equal to 0, cs not equal to 0, and r comma s less than n, then a naught not congruent to 0 mod p square implies that not both b naught and c naught are congruent to 0 modulo p. Suppose that b naught not congruent to 0 mod p and c naught congruent to 0 mod p. Now, a n not congruent to 0 mod p implies that br cs not congruent to 0 mod p, since a n is equal to br into cs. Let m be the smallest value of k such that ck not congruent to 0 mod p, then a m is equal to b naught c m plus b 1 c m minus 1 plus etc. b m minus I c I for some I 0 less than or equal to I less than m. Now, b naught and c m neither congruent to 0 modulo p and c m minus 1 etc. c I are congruent to 0 modulo p implies that a m not congruent to 0 mod p, so m equal to n. This together with the fact that p does not divide cs and m be the smallest number such that p does not divide cm implies that s greater than or equal to m equal to n, that is s greater than or equal to n. from the construction s less than or equal to n, consequently s equal to n, contradicting our assumption that s less than n. Hence, the factorization of f of x in q of x is impossible, that is f of x is irreducible over q. Example 6. Taking p equal to 3 in the Eisenstein polynomial, we obtain that 26 x raised to 5 minus 9 x raised to 4 plus 3 x square minus 12 is irreducible over q. Theorem 6. The cyclotomic polynomial 5px equal to x raised to p minus 1 by x minus 1, which is equal to x raised to p minus 1 plus x raised to p minus 2 plus etc. x plus 1 is irreducible over q for any prime p. Proof. By theorem 5, we need only consider factorization in Zx. Let g of x equal to 5p x plus 1, which is equal to x plus 1 raised to p minus 1 by x plus 1 minus 1, which is equal to x raised to p plus pc1 x raised to p minus 1 plus pc2 x raised to p minus 2 plus etc. p into x plus 1 minus 1 whole divided by x. Then g of x equal to x raised to p minus 1 plus pc1 x raised to p minus 2 plus etc. plus p satisfies the Eisenstein condition for the prime p and is thus irreducible over q. But if phi px equal to h of x into r of x were a non-trivial factorization of phi px in Zx, then phi p of x plus 1 is equal to g of x equal to h of x plus 1 into r of x plus 1 would give a non-trivial factorization of g of x in Z of x. Thus, phi px must also be irreducible over q. Uniqueness of factorization in f of x. We state an important result. Proof is not included in this session. Theorem 7. Let p of x be an irreducible polynomial in f of x if p of x divides r of x into s of x for r of x comma s of x belongs to f of x, then either p of x divides r of x or p of x divides s of x. An application of mathematical induction to theorem 7 yields the following corollary. Corollary 5. If p of x is irreducible in f of x and p of x divides the product r1x into etc. rnx for rix belongs to f of x, then p of x divides rix for at least one I. Theorem 8. If f is a field, then every non-constant polynomial f of x belongs to f of x can be factored in f of x into a product of irreducible polynomials, the irreducible polynomials being unique except for order and for unit, that is non-zero constant factors in f. Proof. Let f of x belongs to f of x be a non-constant polynomial. If f of x is not irreducible, then f of x equal to g of x into h of x. The degree of g of x and the degree of h of x both less than the degree of f of x. If g of x and h of x are both irreducible, we stop here. If not, at least one of them factors into polynomials of lower degree. Continuing this process, we arrive at a factorization f of x equal to p1x into p2x etc. prx, where pix is irreducible for I is equal to 1 to etc. r. It remains to show uniqueness. Suppose that f of x equal to p1 of x into p2 of x etc. pr of x, which is equal to q1 of x into q2 of x etc. qs of x. Equation 2 are two factorization of f of x into irreducible polynomials. Then by the corollary above, p1 of x divides some qjx. Let us assume p1 of x divides q1 of x. Necessary arrangements may be made if needed. Since q1 of x is irreducible, q1 of x equal to u1 into p1 of x, where u1 not equal to 0, but u1 is in f and thus is a unit. Then substituting u1 into p1 of x for q1 of x and cancelling 2 becomes p2 of x etc. pr of x equal to u1 q2 of x etc. qs of x. By a similar argument, say q2 of x is equal to u2 p2 of x, we have p3x etc. pr of x equal to u1 u2 q3 of x etc. qs of x. Continuing in this manner, we eventually arrive at 1 is equal to u1 into u2 etc. ur into qr plus 1 of x into qs of x. This is only possible if s equal to r, so that this equation is actually 1 is equal to u1 into u2 etc. ur. Thus, the irreducible factors pi of x and qj of x were the same except possibly for order and unit factors. Example 7. The factorization of x raised to 4 plus 3x cube plus 2x plus 4 in Z5x is x minus 1 whole cube into x plus 1. These irreducible factors in Z5x are only defined up to units in Z5x, that is non-zero constants in Z5. For example, x minus 1 whole cube into x plus 1 equal to x minus 1 whole square into 2x minus 2 into 3x plus 3 is a unique factorization based on theorem 7 and 8, since 2 is a non-zero element in Z5 and hence is a unit in Z5. Let us summarize this session. In this session, we have discussed division algorithm for the ring f of x and some results and examples that follow from division algorithm. Number of results and examples following the definition of irreducible polynomial have been discussed. We have seen that polynomials in the form Eisenstein polynomial are irreducible polynomials. The result that states the existence and uniqueness of representing a given polynomial into a product of irreducible except for unit and for order have been discussed. Expect you enjoyed the session. Now try to answer the following questions. In assignments 1 to 3, find q of x and r of x as described in the division algorithm so that f of x equal to g of x into q of x plus r of x, the degree of r of x less than the degree of g of x. 1. F of x equal to x raised to 6 plus 3x raised to 5 plus 4x square minus 3x plus 2 and g of x equal to x square plus 2x minus 3 in Z7x. Question number 2. F of x equal to x raised to 5 minus 2x raised to 4 plus 3x minus 5 and g of x equal to 2x plus 1 in Z11x. Question number 3. F of x equal to x raised to 4 plus 5x cube minus 3x square and g of x equal to 5x square minus x plus 2 in Z11x. See you next time. Till then, goodbye.